Welcome to Physics 100. I am Professor Curtis, your instructor for this course, and this is the lecture video for Chapter 13, Liquids. Let's get started. So in the previous lecture, we talked about characteristics of solid materials. Now we're going to look at characteristics of liquid materials. So remember, in the solid materials, the atoms of the material are pretty much tethered in place, and they're vibrating each in their own little position. For liquids, you still got some tethering of atoms with their neighbors, but you've got more mobility. So whereas like solid materials is like everyone staying in their house, now you've got people that are coming out. They come outside the house and they visit with the neighbors, or they run around the backyard, or they're still vibrating there in the same general vicinity, but they've got a lot more mobility than solid materials have. And this is material in the liquid state. Because of this relative motion of the atoms, the liquids lack rigid boundary, and they assume the shape of whatever container you put them into. Liquids, like solids, have density. However, unlike solids, the densities can vary significantly with temperature. So here we have a table listing a number of common liquids and the densities at room temperature. It's important to specify temperature because for liquids, the density will change with temperature. Now, look at the values that we have here. And remember the density activity from the last lecture? Well, look at the numbers here, and how would you say these values compare with the densities of solids that we were calculating earlier in that previous lecture? They're much lower, aren't they? And that's typically what you see with liquids. Now, there's an obvious exception there with the mercury, and mercury is kind of an oddball. It's kind of like, there's a lot of generalizations you can make about the South, but Florida is the exception to most of those rules when it comes to the South. And it's the same thing here. Mercury is one of those exceptional metals because at room temperature, mercury is not solid. Mercury is liquid at room temperature. So that's why you see it there in the list. And because it's a metal, it's got significantly higher density. That's comparable to what you saw with the density for the other metals that we were calculating earlier. But if you take that one off the list and look at what's left, densities are relatively low for liquid materials. And that's typically what you see at room temperature. Now, how much is this density going to change with temperature? Well, let's take a look at water. Water provides a good example of this. And one of the reasons why we look at water is because it's a common material used in engineering systems. I mean, for fluids that are flowing through a pipe, okay, it's not just water that we drink or water that's running through, say, a sewer system to transport waste from one location to another. That water is used as a heat transfer element. And so you've got water that's being heated and cooled. And there's a reason for that, which we'll get into in a future lecture. But because we're using water in, an engineering system, one of the reasons why we do that is because it's abundant. I mean, water is cheap. You want to put something in your system that's going to transport heat from one place to another. You want something that's cheap. Water is a good candidate for that. But notice the differences in density with the water. Now, at 0 degrees Celsius, that's the freezing point of water, we have a density of 0.9998. And then it goes up to a value of 1 at 4 degrees. And then thereafter, as you keep increasing the temperature, the density goes down. Now, that's kind of a weird property of water, and we won't really go into that because it's a little complicated to explain why it does that. But just understand that there's difference in density depending upon your temperature. Now, as you go up, you get to the boiling point of water, which is 100 degrees Celsius. 0.9584 grams per cubic centimeter is your density. Now, you might be looking at this and saying, really? Come on, man. What's the difference between 0.9998 and 0.9584? It's like a 4% difference. It's not going to be anything hugely significant. Well, you wouldn't expect it to be. But as we'll learn towards the end of this lecture, that difference is a really big deal. Now, the other thing to note about density is that notice what happens once you pass the boiling point of water. The density of water goes way down to like 0.0006 grams per cubic centimeter. So the different state of matter plays a big role as far as what your density is going to be. So other liquids are going to show you similar variations, okay? The density is going to change depending upon the temperature. Now, because solids have a rigid shape, it's easy to study the effects of forces on solids. But, liquids aren't as convenient because, again, remember, liquids conform to whatever container you put them in. They don't have a rigid shape of their own. So we need to introduce another concept in order to study the effect of forces on a liquid. And there is a resistant force when you apply a force to a liquid, and it's similarly distributed, but we're going to look at it in terms of per unit area. And this allows us to look at the concept that we call pressure. And that's what pressure is. Pressure is force per unit area. So mathematically, we're going to define pressure as force divided by area. So P is the pressure, F is the applied force, and A is the cross-sectional area. Now, force is typically measured in newtons, area in square meters, so our units for pressure are newtons per square meter. And this is an acceptable way to express pressure, but typically we're going to use another unit that is the equivalent of newtons per square meter, and that is the Pascal. So 1 Pascal is equal to 1 Newton per square meter. Now this is actually a very small amount of pressure. So most of the pressures for systems that we're used to seeing in our common experience are going to be on the scale of kilopascals, where 1 kilopascal is the same as 1,000 pascals, or 1 kilonewton per square meter. Let's walk through an activity to help us understand the relationship between pressure and area. So let's say we have a wood block that's got different colors on different faces of the block. So the block measuring 14.3 centimeters by 8.6 centimeters by 3.7 centimeters. So if we place the block on the table, okay, there's different orientations that we could place the block. We could place it on the brown face or the blue face or the green face. The different orientation is going to give us a different area in contact with the table. And that different area will produce a different pressure that is exerted between the block and the table. So what we're going to do is we're going to calculate the pressure in each of these orientations so we can gain a greater understanding of pressure. Let's walk through the first part of this together. So let's look at the green face first. So if we take that block and put the green face down, so now the force of the weight of the block is being exerted through the green face onto the table. The area of that surface of contact is going to be the length times the width, which for this face is 8.6 centimeters times 3.7 centimeters. If we multiply that out, that gives us 31.82 square centimeters. We also need a force to calculate pressure. So what force is the block exerting on the table? Well, I hope you said it's the weight. That's the weight. The weight of the block is what it's being exerted there against the table. So let's say the weight of the block is 2.13 newtons. So we're going to divide force by area to get pressure. So pressure is force divided by area. Take the force, 2.13 newtons, divide by the area, 31.82 square centimeters, and we get 0.06694 newtons per square centimeter. If we multiply that by 10,000, we can get the units of Pascal, because remember, Pascal is the area of, the unit of pressure that we typically use when we're reporting measurements. And so there's a table there on page 11 in your workbook that you can put in for the first part of this activity. So I take the 0.06694 and I multiply by 10,000. And the reason why we do this is because we have newtons per square centimeter, but a Pascal is a newton per square meter. So we've got to change the square centimeters to square meters. And that's why we're multiplying by 10,000, because there's 10,000 square centimeters for every 1 square meter. So we multiply 0.06694 times 10,000, and we get 669.4 Pascal. This is then the value that you need to place there in your table in your workbook. There's also a spot there for area, so the 31.82 square centimeters is also going to need to go there. All right, so here we go. Let's run through the second part, and let's see if you can actually do this on your own, and then I'll run through it. So stop the video here, see if you can run through this on your own, and then start the video back up, and we'll see how well you did. All right, let's see how you did with this. So remember, first we need to calculate the area, so length times width. Here, this blue side of the block, 14.3 centimeters times 3.7 centimeters, gives us 52.91 square centimeters. The force that we're going to use to calculate, has that changed at all from the first part of the problem? No, it hasn't changed at all. It's the same block, so it's going to have the same weight, and therefore the same force exerted against the table. So the weight of the block is still 2.13 newtons. So we're going to take that force, divide by area, and that gives us pressure. And then multiply by 10,000 to make sure our units are right, and now we've got pascals. So force, 2.13 newtons, divided by our new area, 52.91 square centimeters. Now we've got 0.04026 newtons per square centimeter. We multiply that by 10,000 to give us pascals, and we come out with 402.6 Pascal. So remember to put this number as well as the area for this part there in your workbook on page 11. One more part, because there's one more side that we haven't examined. It's the brown side. So go ahead and see if you can work through this on your own, and then when you get done, come back to the video, start it back up, and we'll see how well you did. All right, go ahead and start. Let's get this started, see how well you did with this. So area is length times width, which for the brown face, 14.3 centimeters times 8.6 centimeters to give us 122.98 square centimeters. Again, it's the same block, so we've got the same weight, 2.13 newtons. We divide force by area to get pressure, then multiply by 10,000 to get units of Pascal. So force per area is pressure, 2.13 newtons divided by 122.98 square centimeters gives us 0.01732 newtons per square centimeter. We multiply that by 1,000 to get units of Pascal, and we get 173.2 Pascal. So here's what you should have in your table. So 3 areas, 3 pressures, and these are the values that we should have there in the table. Again, keep in mind that 1 newton per square meter is the definition of 1 Pascal. So notice that we always kept the force constant. The weight of the block did not change. So the only thing that's changing here is the area. What area is producing the largest pressure? Is it the smallest area or the largest one? Well, if you look at your numbers here, you can see that the largest pressure comes with the smallest area. The largest pressure is produced with the smallest area. The The largest pressure is produced with the smallest area. The smallest pressure is produced with the largest area. If you think about it, this should make sense. Because pressure is just distribution of a force over an area. So if you have a smaller area, that force is going to be divided up in less ways than if you have a larger area. Because if you have a larger area, that force gets distributed amongst more area. And so the actual force that any portion sees is much smaller. Whereas with a smaller area, you divvy it up. Now the divisions there across the area, it's going to be bigger. Every portion of the area is going to see a bigger portion of that force, and so you get more force. So you get a higher pressure with the smaller area. And so that's how the numbers go. And if you think about it, it should follow out and make sense to you. So large pressure comes from small area. Small pressure comes from large area. Pressure works the same way in liquids, but it's often more convenient for us to use a different form of that pressure equation. So with some algebraic manipulation, we turn P equals F over A into P equals rho GH. So P is still pressure, rho is going to be the density of your fluid, G is the acceleration due to gravity that we've seen before, and H is the height, or rather the depth of the object inside your liquid. This form of the equation is more convenient to use for liquids. And there's reasons for that. Density is typically a constant for given application. And, the acceleration due to gravity is a constant. That number doesn't change. And so that means all we really need to know in order to get the pressure is the depth. How far below the surface of the liquid are we? You don't have to know this derivation. It's not calculus based, but it is kind of interesting for those students who are curious about, well, where did we get that new equation from? How did we manipulate that original pressure equation to get this specialized form for liquids? And if you're interested, this is how we did it. So I'll let you look at this on your own. But the only thing you really need to know is the equation there in the box, P equals rho GH. You need to know how to use that equation when we're dealing with pressure in liquids. This is a very significant equation because really all it's saying is that pressure is a function of only one thing, and that's the depth, how far below the surface you are. So it says at the same depth, the pressure everywhere at the same depth is the same. So it doesn't matter what the size of the water source is, the shape of the water source, none of that plays out because, see, there's no representation of that there in your equation. The only thing you have, pressure equals rho, which is a constant, it's density, and G, that's also a constant, acceleration due to gravity. So the only thing that varies is the height. And that's it. There's nothing else in there. So it's depth alone that determines what the pressure is. And it's same for all points at that depth. So in this way, pressure is kind of like what we saw with potential energy. Remember, potential energy, path independent. Doesn't matter how we get the object to its final position. All that matters is what final position does it have. How far above the ground is it? Same sort of concept here, except with liquids, it's how far below the surface you are that determines your pressure. So water pressure in the same container is going to vary only with depth. And so if we have, say, a container with 3 holes in the side, and we've got water in that container, then you could see that the pressure is going to be greatest at the bottom because the bottom is the deepest. It's the deepest part. And so the deeper you are, the more pressure you have. The more pressure you have, the more force you have with the water jet coming out of the hole. So there at the top where we don't have as much depth, we don't have as much pressure, and therefore it's just kind of petering out there at the top. But there at the bottom, the pressure out is much higher, and so therefore the little stream of water coming out is significantly stronger. And again, this is just a difference in pressure. So pressure is going to be a function of depth. and nothing else. That's the only thing that matters is the pressure. It's its depth. So this brings us to the concept of buoyancy. Have you ever noticed that something that's in the water seems to weigh less? Why is that? What is it that gives it that effect? Well, this is where buoyancy comes in. What forces are acting on an object under the water? Think about it. What forces do you have? Well, you've got the weight of the object pushing down. And so if the object appears to weigh less in the water, that must mean you have another force acting in the opposite direction, pushing back up. And this is the buoyant force. This is what buoyancy is. So buoyancy is the effect of your buoyant force. It results from the differences in pressure on the top and the bottom. So on the top of your object, you've got a certain force acting at it. That's the pressure at that depth. But you've got a much higher pressure on the opposite side of the object, because there on the bottom of your object, you're deeper. And so deeper, more depth means you've got higher pressure. Higher pressure means more force. So higher force there on the bottom than you do on the top. And so the net result is a buoyant force that pushes up to resist the weight of the object. And that's why objects appear to weigh less in the water. Archimedes was a scientist, and he's a Greek inventor, even though he wasn't living near Greece. He's living on the other side of the Mediterranean there in Carthage, which is basically off the northern coast. It's like Tunisia, Libya. That's the part of northern Africa. And so he's basically living here. And Archimedes was a pretty curious guy. He was clever in a lot of ways. There's a lot of great stories I could tell you about Archimedes, but I'll let you ask me about them if you want to hear them. So, yeah, Archimedes was studying a lot of things, and he had this effect of buoyancy related in a principle which bears his name, the Archimedes Principle. And it's basically this: an immersed object is buoyed up by a force equal to the weight of the fluid it displaces. This means that the buoyant force, is going to be equal to the mass of the fluid it displaces times the acceleration due to gravity, because that's the weight. The weight of the fluid is the mass of the fluid times the acceleration due to gravity. Well, the mass of the fluid is just the density of the fluid multiplied by its volume. So the buoyant force is equal to the density of the fluid it displaces times acceleration due to gravity times the volume of the object. Because the volume of the fluid displaces equals the volume of the submerged object. So we're talking about an object that's completely under the surface of the water. Either volume can be used to find the buoyant force. If your object is not completely submerged, so only a part of it is below the surface of the water, then you want to use the volume of the object that is below the surface of the water. So whatever is above the surface of the water does not enter into the calculation. Typically, we're going to be looking at objects that are completely submerged, so you take the entire volume. But this is where, floating objects come in. This explains why, you can build these massive boats made of steel, which has a density much higher than that of water. And yet, these steel ships will float. Remember that a floating object will displace a weight of water equal to its own. Or put another way, the buoyant force pushing an object up equals the weight of the object pushing it down. So it's in equilibrium and it doesn't go anywhere. Put yet another way, the density of the entire object has to be equal to or less than the density of the water. Otherwise, the object will sink. So the example that you see there on the screen, you've got a block of iron, and the weight of that iron is a vector that points down, and the buoyant force is pointing up, but it's a very small buoyant force because the density of the object, of the water that's displaced, multiplied by G, multiplied by the volume of the block, is not as large as the weight of the block itself. So the net force is a force that's pointed down, and that's why the object sinks. Take, for example, a steel ship, on the other hand, and you've got the volume of what's actually below the water line. So you've got the iron, yes, which is more dense in the water, but then you've got everything else, including the air that's inside the ship. And so you take that into consideration, and your density is going to go way down, and it'll be less than the density of the water. And therefore, the buoyant force of that ship is going to be greater than the weight of the iron that's forming the hull of the ship. And guess what? The net force is now force pointed up, and that's why the ship does not sink. Now, of course, if you've got a leak in the boat, then it starts that the air that's giving you the lower density is going to be replaced with water. You get enough water, and now your density becomes greater than that of water, and your boat will then sink because the buoyant force is going to be less than the weight of the boat. Notice that in an earlier activity we talked about how pressure will change if we keep the force constant and change the area. Well, what happens if, we keep the pressure constant and change the area? What happens to the force? Well, the force is going to change. And the way in which it changes is going to lead us to what's called Pascal's Principle. And this is named after the French scientist Blaise Pascal, who lived in the 17th century France. And it was his work that gives us the answer. A change in pressure at any point in an enclosed fluid at rest is transmitted undiminished to all points in the fluid. So if we have fluid that's entirely enclosed, and we put pressure on one end of the enclosure, that pressure is going to be equally distributed all throughout the liquid. Pascal's principle allows us to magnify smaller forces into larger ones, and this is the principle behind the syringe and the hydraulic press. So here we have an example of a hydraulic press. If you've ever seen the car lift in a mechanic shop, that's a good example of a hydraulic press. And this is the same principle upon which it works. So we can take a little force, so a little weight, over a small area, and that same pressure is going to get distributed all throughout. So that same pressure distributed all throughout the liquid, it comes over to the other piston. The same pressure now is distributed across a larger area, and so to have the same pressure, you have to have a proportionately larger force. So we can turn a little force into a larger force with Pascal's principle. Mathematically, we represent Pascal's principle with this equation. F1 over A1 equals F2 over A2, or more commonly, F1 A2 equals F2 A1. So the 1s and the 2s represent the different pistons in the hydraulic pump. So there's piston 1 and there's piston 2. And normally we label one of these pistons as an input piston. So this is where we put the force in, and then we get a force out with the other piston. So one piston is the input piston, and that's typically piston 1. And then the other piston would be the output piston, and that's typically piston 2. So suppose we have a hydraulic pump with an input piston area of 8 square centimeters and an output piston area of 40 square centimeters. In your workbook, I want you to answer the following questions. If you apply a 20 Newton force to the input piston, what force does the output piston produce? Second, if you apply a 10 Newton force to the input piston, what force does the output piston produce? And third, is the force you output being changed by a set amount or proportion? If so, what is it? So go ahead, stop the video here, and then take a moment to answer these questions. And then when you get done, come back to the video and we'll see how well you did. Okay, let's see how well you did with this. So first question, if you apply a 20 Newton force to the input piston, what force is output? Well, with 20 Newton force input, we're going to take our equation, F1 A2 equals F2 A1. We're going to substitute in what we know. So there's 20 newtons on the force that's inputted, so that's F1. The output piston has an area of 40 square centimeters. The output force, F2, is what we're trying to find out. And the input piston area, A1, is 8 square centimeters. So now that we have what we know, we take the 20 times the 40, that gives us 800 Newton square centimeters. And then we're going to divide both sides by the 8 square centimeters. So we get F2 all by itself. 800 Newton square centimeters divided by 8 square centimeters is 100 newtons. So that's the force that's coming out of the output piston when we put 20 newtons in. The second question, if you apply a 10 Newton force, what is the output? So we're going to follow the same procedure, start out with our equation, substitute in what we know. So notice the 20 newtons is now 10 newtons. Everything else is the same. So 10 times 40 gives us 400. Divide both sides by 8, and we get 50 newtons for the output force. So is the force you output being changed by a set amount or proportion? And if so, what is it? So notice what happened. The force that went in is 20. The force that comes out is 100. If we take half that force going in, we get half the force coming out. So yes, there is a set amount or proportion. And notice that the output force is always 5 times the input force. So 20 times 5 is 100. 10 times 5 is 50. So we're always getting 5 times out what we put in. That's because the difference between the piston areas is a factor of 5. Notice that the one is 40 and the other is 8. 8 times 5 is 40. So it's that same proportionality between the piston areas that is kept between the forces. And that brings us to the end of this lecture. I hope you found it helpful. Thanks for watching, and we will see you in the next video.